Today we'll start with a new chapter. This is chapter 5. Okay. So what we're going to see here, chapter 5 is it's called reduction of multiple subsystems, and we're going to see two types of reductions. One is block diagram reduction, and then we're going to see signal flow graphs. Okay. So under block diagram reduction, so you see these are, what you're seeing here is 1, 2, 3, and 4. These are the components of a block diagram. Okay. Try not to confuse this with Simulink blocks. They look similar. You can find all of these blocks in Simulink, okay, or you can emulate all of these blocks in Simulink, but all the blocks of Simulink are not here. You understand? So you see, you have seen source and sink, right, in Simulink. You'll see summation blocks. You'll see pick-off points. You have seen G of S, right? What was this in Simulink? It was the LTI system, you remember, from the control system toolbox, and you had signals coming in and going out, right? So these are the blocks, the 4 blocks on which the block diagram reduction or block diagram math is based on. Okay. We look at 3 topologies for interconnecting subsystems. Now you have to understand the purpose of something like this. When you are building your system, each of this system, each of the component of any physical system has a transfer function, and we have looked at that. The transfer function of a spring, what is the transfer function of a spring? Just K, right? Whatever the spring constant. The transfer function of a spring is K. What is the transfer function of a damper with a damping coefficient C? What is it? Huh? Damping coefficient of a damper, the transfer function of a damper with damping coefficient C or D, what is it? DS, right? FVS. It is not C of S, it is CS, okay, or D of S. If it's a damping coefficient is C or FV, it is FV into S, right? This transfer function of a mass of mass M, what is the transfer function? Ms square, right? So it is Ms square CS. So these are the transfer functions. So you can take what you have done, you have looked at spring mass damper systems, different configurations. You can have such a thing for each component, and you combine them, right? And you build an equivalent transfer function of the system. We have looked at equivalent transfer functions, but we can look at each system, each component of a system, and build them as blocks to get a complete transfer function. And this is the block diagram. If you're doing very, if you're designing elaborate systems by joining like Lego blocks, right? something like this would be of significant use. And Simulink is kind of based on this model. You see that? You have already looked at Simulink, right? You have moved around the system, moved around subsystems to get, correct? So we look at three topologies for interconnecting these subsystems. So you have, the first one is the cascade form, okay? It's very simple. You have G1 of S So here, you can say the signal here is x1 of S, the signal here is x2 of S, right? x1 of S over Rs is G of S or G1 of S, okay? x2 of S over x1 of S is G2 of S, and C of S over x2 of S is G3 of S. Okay. So if you see such a block, the equivalent transfer function would simply be, so what is the equivalent transfer function of this system? Is C of S over R of S, okay? It has to be C of S, R of S. The input and output, all these are intermediate signals, right? You can see that? For example, when you type on your keyboard, that is this signal, okay? Whatever you're seeing on the screen is something like this signal. But that doesn't mean there is nothing in between, right? There are many, many components it goes. So you have to understand, you have to just think about intermediate signals, right? So your C of S mathematically is what? It is, right, x1 of S over R of S into x2 of S over x1 of S and x2 of S, sorry, C of S over x2 of S. So you have this cancels, this cancels, this cancels, this cancels, right? So your C of S over R of S is essentially G1 of S, G2 of S, G3 of S, right? And if you were to write the equivalent block, you will have something like this. You have just one block. You have G1 of S, G2 of S, G3 of S, an input coming in and an output. Okay. So this is the cascade form. The second one is parallel form. Okay. Parallel form is something like this. So whatever signal you apply, the same signal is going to each block. Okay. So here x1 of s over r of s is equal to g1 of s. Okay. x2 of s over r of s is equal to, you have, let's say you have plus, let's do plus minus plus. Okay. If you look at what C of S is, what is C of S? C of S, you can simply say it is x1 of s plus, minus x2 of s plus x3 of s, right? Correct? So you see, it is this signal plus this signal. You see it? C of s is essentially all these three signals summed up or added or subtracted, whatever, take into account the minus and positive sign. Okay. If you have a summation block, we saw the summation block here, right? Huh? Yeah, that's a summation block. The signals get added. When signals join, they cannot multiply. Okay?
Yes, but when it hangs the second signal is deleted.
It's just randomly taken signal. But it can, for a defined system, the signal will be, you'll know whether it's positive or not, positive or negative. But this is just a random selection, a random sign. Okay. So let's skip this thing. Let's just do plus. Okay. So it's not very confusing. So we'll just do this. Right. So what is this? X1 of s is r of s into g1 of s plus r of s into g2 of s plus r of s into g3 of s. Okay. So therefore, C of s over r of s is simply g1 of s plus g2 of s plus g3 of s. Okay. The equivalent block is g1 of s plus g2 of s plus g3 of s. Okay. I have r of s. This is C of s. Got it? This is the parallel form. And finally, the third one, so you can take this as 1. And so erase this. one is feedback form. Okay. So what you have, the system here looks something like this. This is also representative of a feedback control system, okay? And typically this is how any of the control systems you design are going to look like. So just take a minute to understand what this is. You know what a transducer is? You understand what a transducer is? What is a transducer? Amplifier is a kind of transducer, is a type of transducer. It transduces a signal. You can say it changes the signal. Something like that. So, for example, accelerometers. If you look at accelerometers, what do they sense? What are pure accelerometers? They are right. So they are based on F is equal to ma. They are based on this law. They actually sense force. So force and then convert that to acceleration because the mass is known. Especially the MEMS. You know what MEMS is? Micro electromechanical systems. MEMS. So that all the tiny sensors, all the sensors in your cell phone, you know your cell phone has accelerometers, right? So when you turn it, the accelerometer senses which direction the acceleration is, and that's the reason your screen also changes. So it is those are MEMS sensors. Those are very, very, what it means is they are micro electromechanical systems. So there is a mechanical component and then there is a electrical component. Most modern sensors are electrical sensors. Okay? So if they're electrical sensors, what are strain gauges? Strain gauges are, do they sense really strain? No. They sense change in voltage, right? So that change in voltage corresponds to its strain, correct? So that is kind of a transducer. It senses voltage, purely it senses voltage. But then you can relate that to strain. You can say this is the change in voltage. This must be the change in resistance, right? And then you say you correlate that to change in strain. So that is a transducer. Transducer is something which all your AC units are transducers. You cannot really sense temperature, right? So again, how would you sense temperature if you were given an option to design a temperature sensor? What changes with temperature? Right. But from electrical perspective, does the resistance of this thing change with temperature? Yes. It changes, right? So you can kind of say, I'll sense the resistance and then correlate that to temperature. There is a resistance to temperature curve. You can correlate that to and change. That would be a transducer. So this here is, think of this as a transducer. The H of S is a transducer. So what's happening here is, this is the plant or process, okay? It includes the control system and the actuators. Now, you're inputting a signal. The output is being sensed and transduced and fed back into this system. So think about this. You're giving an input, right? If the error between this and this is 0, you don't want it to do anything, right? If the temperature, for example, if you're thinking about the temperature, it senses resistance. It transduces that to temperature, okay? And if the temperature difference is the same, this is the error signal. E of S stands for error signal. If the error signal is 0, you don't want to do anything to the system. It's already in a controlled phase. But you want to keep feeding back the output to know that you've reached what you desire. You see it? This is a feedback. This is a closed loop control system. Okay? Most of your control systems are based typically, especially your aircraft systems and spacecraft systems. Can you think about an open loop control system for a spacecraft? There is, what do you want to control in a booster? Think about what you want to control. Huh? Flow of fuel. Then you're not really controlling flow of fuel. Okay, right. So that is, you're right. Flow of fuel, it's time based, right? So you know that you'll orient the spacecraft in a particular direction, and then say you predetermine that this much amount of fuel diffused will give you this much amount of change in velocity. Then you do a time-based control of the fuel. Okay. The other thing you can think about is, let's say if you're trying to stabilize a spacecraft, how would you passively stabilize a spacecraft? Passively. Huh? It's not passive. Passively, how would you do it? Stabilize in the sense, when I talk about spacecraft, it is not rocket. Rocket is not a spacecraft, okay? Right, something which is in orbit. Spacecraft is, even a space shuttle is, although, let's say the spacecraft is tumbling, okay? The gyroscope? Gyroscope, what will happen is gyroscope will always keep whatever is mounted on its platform. If the spacecraft is moving, the gyroscope will maintain the orientation of the whatever is mounted on that stable. But think about a spacecraft which is tumbling, and you have a, let's say, a permanent magnet in there. What it will do? It will try to align itself with Earth's magnetic field. Right? It will try to align with itself. It's like a freely suspended needle. What it will do? If you just disturb it, eventually it will align with Earth's magnetic field. That is passive stabilization. That's the open loop control system. So you don't have any transducer in that. But if you have an electromagnet, what will you do? You will sense, right, what direction it is orienting, and then change the field strength of the electromagnet. That is active. That is feedback control system. You see it? Okay. So this, here you can say, what is the feedback form? Again, we need to figure out what C of S over R of S is. Okay. So you can say, C of S is essentially equal to E of S into G of S. Okay? You agree? Right. So C of E of S is R of S minus C of S into H of S. Right? If I cut this signal, if I do this, I have to add a C of S here. You see what I'm doing? Right? Because that signal is getting multiplied. That's a pick-off point. It's getting multiplied by the output. Right? Now you see C of S into H of S is what is going in the summation block. But this is negative. Okay? Mostly it is negative because you think about it. Makes sense, right? Because you want to see the difference in the output and input and then drive that to 0. Okay? So you have this. So you have R of S and G of S minus C of S, H of S into G of S. Or C of S is equal to C of S into 1 plus G of S, H of S is equal to R of S into G of S. Okay, so I just moved this to left hand side and took C of S common. Okay, you see this? It's fairly simple. I moved this on the left hand side. So C of S, therefore C of S over R of S is equal to G of S over 1 plus G of S into H of S. This is the feedback form. Anytime you have a feedback form, you need to either be able to derive this or remember that C of S over R of S is G of S into GS over 1 plus GSHS. Okay? Can we quickly do an example? You guys have time or you have another class? Just give me 5 to 10 minutes, we'll finish off one example. You have a class? Okay. Huh? You have a class from 12 to 1? Huh? That's fine, we'll do it next time.